Hey everybody, welcome to video number 2. We're going to start here with number 6, and we're going to be doing long division because my divisor is a quadratic and we cannot do synthetic division unless this is linear. So I'm going to set this problem up and I want to show all my steps so that you can check your work just in case there was a mistake in there. So how many times does 2x squared go into 6x to the 4th? Well, if I divide 6x to the 4th divided by 2x squared, I will be left with 3x to the 2nd power. Then if I multiply back, 3x squared times 2x squared is 6x to the 4th. 3x squared times negative 1 gives me negative 3x squared. If I change the signs on both of those, this becomes a negative and this becomes a positive. You could put a 0 here if you'd like, but at this point we want to bring everything down. So we have 10x to the 3rd, combine these, plus 16x squared minus 5x plus 2. So here we go again. How many times does 2x squared go into 10x to the 3rd? Well, it goes in 5x times. So I'd write a 5x up here. 5x times 2x squared is 10x to the 3rd. 5x times negative 1 is negative 5x. Subtracting. So this becomes a negative, or the subtract becomes a negative. This becomes a positive. Carry down the 16x squared. These two do cross out, but I'm going to put a 0x as a placeholder just in case, and then bring down the 2. I can go for another round. 2x squared does divide evenly into 16x squared, 8 times to be exact. 8 times 2x squared is 16x squared. 8 times negative 1 is negative 8. Subtract, subtract. So I have 0x plus 10. 2x squared cannot divide evenly into 0x or 10. So 0x is really just 0. So it looks like my remainder is 10. So my final answer, my quotient, is 3x squared plus 5x plus 8. I'm running out of room, so I'm going to write it below, plus the remainder of 10 over the divisor of 2x squared minus 1. Now in your answer, make sure it's all one straight line. I just ran out of room on my screen. The next example, find a polynomial function that has the following zeros. So here you want to think backwards. If you were factoring and you got a root or an answer of 0, that really came from x minus 0, which is really just x. And we'll talk about that in a second. If you got a root of x minus 7, that came from x plus 7. And if you got a root of positive 5, that came from x minus 5. And all of that is going to equal my function. If I want to simplify that a bit, x minus 0 is really just x. So I'm going to write my answer a little bit more simply here. And this would be my answer if the directions had said leave it in factored form, but it didn't. So I'm going to keep multiplying it out. I'm going to distribute the x in first. So this would become x squared plus 7x. And then I still need to multiply that by x minus 5, and that still equals my function. So if I multiply all terms by each other, I would have x to the 3rd minus 5x squared plus 7x squared minus 35x, which would simplify to be x to the 3rd plus 2x squared, because I combine these, minus 35x. So this would be my function f of x if we multiply it completely out. X to the 3rd plus 2x squared minus 35x. And this makes sense to me because we talked about that if there's 3 real roots, it's most likely coming from a cubic function. Number 8 asks, is x equals negative 2 a solution to the polynomial, and how do you know? Well, a solution is another name for an x-intercept or a root, or you can even think, is it a factor of this polynomial? And what you could do, one way, is you could do synthetic division to see if your remainder is 0. If your remainder is 0, then x equals negative 2 must be a solution because it's initially a factor. So let's try it. If I plug negative 2 in and I be careful with my lead coefficients. 5, we need 0 for x to the fourth, -1, 0 for x to the second, 2, and then -10. If I follow my synthetic division process and bring down the 5, multiply, get -10, combine, multiply, combine, multiply, combine. -38 times 2 gets me a positive 76. Combine down, get 78. 78 times 2 gives me -156, which means that my remainder is -166. So it seems like this is definitely not a solution to the polynomial because my remainder here is not 0, and that way it's not a factor. So I'm going to say, is it a solution? No, since the remainder is not 0. Another way you could do this problem is you could plug -2 into this function, and if you did, you would get -166 again, which again would tell you that your remainder is not 0. So it cannot be a factor, cannot be a solution. Number 9, use the following function to first find all possible rational zeros. And this is the rational root test when we take plus or minus p over plus or minus q. P is the last term in the polynomial, and q is my lead term. So what we need to do is think about all the factors of 10. And the numbers that divide evenly into 10 are 1, 2, 5, and 10. And in my denominator, there's really a 1 in front of here. So my only factors of 1 are positive and -1. So my possibilities for roots, these are all not actual roots, but possibilities would either be positive or -1, positive, -2, 5, or 10. Because if I divide all of these by 1, these are my final answers. So I have 8 possibilities. And you might remember from the 8a.5 videos that we are going to use these when we use our calculator to our advantage. And what I've already done is I've graphed the polynomial here in Desmos. I have it here somewhere. Here we go, in Desmos. And you want to look at your graph and see if any of the roots that are here are also in your list of possibilities. All my roots were nice. So I'm going to scan, and I notice, so that's not a nice root. -2 is a nice root. This is not a nice root. So -2, 0. Let's look back. Yes, I had -2 as an option. So let's use it. Because the reason we want to list all of these is my goal is to get this function to eventually become a quadratic so that I can factor, use the quadratic formula, square roots, however I want to solve this. So if I think that -2 is an answer, it's an option, and I saw it on the graph, I'm going to bring down the lead coefficients from my polynomial. And the reason I'm doing synthetic division is because my root really comes from x plus 2, which is linear, so synthetic division is the fastest way. Bring down the 1, multiply, combine, multiply, combine, multiply. I got a remainder of 0, which means that -2 is a factor, which means this is definitely one of my answers, so awesome. Because I started with a cubic function, the synthetic division made this quadratic. Specifically, it made it x squared plus 0x minus 5. And if I want to keep solving this, I would set that equal to 0. So I have x squared minus 5 equals 0. And if I solve that, that would be x squared equals 5, which means that my 2 other roots would be positive and negative root 5. So if I listed my roots, I would have -2, 0 as my first one. And then I would have positive root 5, 0, and negative root 5, 0. Now part C I like because it's based on what you just found. This function was originally written in a format that was not factored, but now that we found the roots, we can rewrite the function in terms of the roots we just found, which is why it's called completely factored form. So I'll call this function g of x, Even though honestly it's the same function, so you could probably call it f of x, but nonetheless, think backwards. If my root was negative 2, it came from x plus 2. If my root was positive root 5, it came from x minus root 5. And if it was negative root 5 as my root, it came from x plus root 5. And all of these are in factored form, so that would be my answer for part C. The next examples for number 10 are writing things with a complex number, a plus bi, and these are from your last cumulative number 1 test. And they are here on purpose because we both feel that using more practice with this is a great idea. And here's what I want you to remember, that I is the same thing as the square root of negative 1. If you square both sides, I squared is equal to negative 1. I cubed would then be equal to negative I, because you're multiplying by an I here, and I to the 4th is equal to 1. As long as you know these four, you can be set for these problems, because for part A, if you don't like I to the 9th, let's split it into something that we do know. I like the fact that I to the 4th equals 1, so I'm going to think of I to the 9th as I to the 4th times I to the 4th times another I. You might remember from your exponent rules in algebra that when you have the same base, you add the exponents to get the 9. So if I keep simplifying this part, this is really negative 4 times 1 times 1 times I. And that is really just negative 4I. If I look at the second part, plus 7 times, not adding. I remember on the test some of you said this was adding, but this is multiplied by the square root of negative 9, which is imaginary 3i, and then finally plus 8. So I really have negative 4i plus 21i plus 8. So if I want to write my answer as a complex number, a plus bi, the real part 8 goes first, and then the 21 minus 4 combines as a like term to get me a plus 17i. So my answer as a plus bi is 8 plus 17i. Part B, what we need to use is the conjugate. So just like radicals, we can't have imaginaries in the denominator. So we multiply top and bottom by the conjugate in the hopes that we get rid of the i's in the denominator. So let's see if it works. If I distribute the 4 in on top, I would have 20 minus 8i in the numerator. And then if you remember this is a binomial times a binomial, we'd have to do FOIL here. So then 5 times 5 would get me 25. 5 times negative 2i is negative 10i. 2i times 5 is positive 10i. And then 2i times negative 2i is negative 4i squared. Please remember that you are multiplying the 2 times 2, and the I times I does get you I squared. Very common mistake to forget that. Good news, in the denominator, these do cross out, so my i's are disappearing. So I have 20 minus 8i in the numerator, and in the denominator I have 25, and then this is really negative 4 times I squared, which is negative 1. So this really ends up being plus 4 in the denominator. So I have 20 plus 8i all over 29. Now if I want my answer to look like a plus bi, let me separate it into real and imaginary. So we could write it as 20 over 29 plus 8i also over 29. That is the perfect answer in the perfect format for a complex number. Feel free to watch any of these examples again if you want to hear me explain it again. We have a few more. Number 11 is another example that was from your last cumulative test, and again it is here on purpose because it's based on what we saw when grading your last test. And this is another one that I'm going to start in the next video to make sure there's enough time to explain. And in the last video we're going to do 11 and 12, and that's it. Alright, so stay tuned. I'll see you in video 3.